Till now, we've seen a few components of the microscope. We've seen the types of electron sources, the construction of sources. We've seen the lenses or the imaging system that is used in the microscope, construction of lenses, kinds of lenses, deflector coils, and so on. We've drawn some analogies with basic wave optics on trying to understand how a lens functions, what is happening at the object plane and the backfocal plane, and how you switch from a real space to reciprocal space or from spatial domain to frequency domain. And before we go further into understanding the image formation physics and the mechanisms, which is closely related with the modes of imaging and modes of operation in a microscope, I'll just complete a few other important aspects which is related to a few important components which we practically use, like the apertures, the recording systems, and also a little bit on the specimen preparation and the kinds of specimens that are used. So once we understand this, we'll understand the electron beam and material interaction, and then revisit the fundamentals of scattering and how the intensity of the electron beam changes after a scattering phenomenon, and how the phase changes as a consequence of propagation of an electron beam through the microscope. So one of the important and often neglected components, or not completely understood components, and one of the most sensitive components in electron microscopes are these apertures. If you are not very careful and if you are using manual alignment tools, it is very easy to misalign the apertures. If you have motorized apertures as well, you might end up displacing the aperture so far away from the mean position that you may end up creating some kind of aberrations, which I'll not go into right now, but this is one of the sensitive parts which can really be misaligned, and you may end up blocking the beam without knowing what the problem is. So let us look at how these apertures look like. First of all, what exactly is an aperture and why should you use them? If anyone has used a DSLR camera, you might know that there is something called as changing of the aperture size. You want to make the aperture wider when you want to focus on a very small object. For example, when you are obtaining a portrait mode image, you open up the aperture more, and by controlling the size of aperture in a photographic camera, you are kind of playing with the amount of light that is actually going and hitting your sensor there. Likewise, in an electron microscope, by controlling the size of the aperture, you control various details within a microscope. For example, if I'm collecting the information from the forward scattered electrons, I can use an aperture to restrict only one portion of the forward scattered electrons to go through and form an image. I can selectively choose one specific set of forward scattered electrons to form special images. This is called as weak beam or dark field imaging mode. Or if I allow the higher order scattered electrons to not go through and form an image, I can improve the contrast. Also, when I use the aperture to form a probe, the size of the aperture is actually controlling my convergence angle of the probe. This in turn has an effect on the resolution in STEM mode. So apertures are quite important. An often confusing term that we use in electron microscopy is, you say, inserting an aperture. In fact, an aperture is simply a hole. The aperture is a hole in a metallic plate, which is actually called as a diaphragm, and depending on the sizes of these apertures of various dimensions, you are inserting either a smaller or a larger aperture. So let me show you how these apertures look like and how do they act So for this I will look at simple schematic ray diagram and show you an image of how the aperture looks like. So let us say here is my specimen. The forward scattered electrons can go through anywhere over the hemisphere here. By choosing a diaphragm like this, typically a strip aperture or a diaphragm looks like this, I can choose one selective set of forward scattered electrons to go through and form an image. Likewise, if I place an aperture in front of the condenser lens, I can also choose I can restrict the angle of convergence I have here to form a probe. So this is extremely important to actually improve the resolution in STEM mode, or here specifically to choose a specific set of forward scattered electrons and form an image, it becomes important. So if you look at these apertures here, can you guess the approximate sizes? It is rather surprising that within a microscope which is about 2 meters high and column which is approximately 1.5 feet in diameter, the aperture is only along the optic axis, which is having a bore, or the column of the microscope has a bore of a few millimeters, and this aperture is ranging from a size of 100 or so. If I think about the first condenser apertures, these are of the order of 2000 microns, and the second condenser apertures are somewhere 200, 100, 70, 40, 50, 10 and so on, and the selected area and the objective apertures range anywhere between 100 to 10 micrometer. Why are these sizes so small? If I think of the maximum possible angles of scatter I have in an electron microscope, they are usually within the range of 10 to 20 milliradians. So all the forward scattered information, almost 95% of it is restricted to a very narrow domain, and that is why the apertures are so small. And this is precisely the reason why I was mentioning that it is very easy to misplace this. When we look at different modes of imaging, when we start seeing demonstration of various modes such as diffraction or in STEM, we will see the use of these apertures. So for now, the main takeaway is aperture is actually a small hole which is placed in a diaphragm. Typically these are platinum or tungsten strips in which small holes are present, or molybdenum, because you use a heavy atomic weight element so that whatever electrons are beyond this hole are sort of restricted with the heavy atomic weight element. And the main important role the aperture plays in is you can have a control on the collection angle or the convergence angle when you are doing various modes of imaging. So here is how a typical aperture holder looks like in a manually controlled microscope, and you insert this and you have options to move the aperture inward by turning one of the knobs and to displace the aperture in x and y plane. So if y is the movement inward, the x is the displacement. So you use these two knobs together to actually move the aperture. We will look at more of this when we start seeing the practical hands-on sessions at the microscope. The next important component is the detector or the recording system. There are various detectors and recording systems available. Predominantly These started with photographic plates or photographic films, where you typically have silver nitrate film, and on exposure to the electron beam, this undergoes a reaction and you fixate the intensity distribution on a photographic plate. And then we had something called as image plates, and then we had the CCD cameras, and then you also have something called as CMOS cameras, and now direct electron detection cameras as well. Depending on the kind of camera you use, you have something called as the dynamic range, that is the maximum range of intensities you can actually collect and record and save. In fact, the old school image plates had an excellent dynamic range, and these were the best recording media for diffraction patterns. It is extremely important in diffraction patterns because the central spots are having the highest intensity, and some of the farther weaker spots do not have such high intensities. So this range of intensities that I can record on a recording medium is actually a dynamic range. And if I talk about the principle of CMOS detectors or CCD cameras, the idea is simple. You are converting the electric signal from the electron beam to some kind of a digitized signal. So when the electrons hit the pixels on a detector, I am converting this into an electric pulse, and I am recording it as, depending on the kind of camera you have, you are recording a grayscale image, and the intensities are scaled from 0 to 255, or depending on the dynamic range of the camera, you get varying values of intensity. And let's have a look at how these detectors look like. And before I go into the functioning of a CCD camera or a CMOS camera, let us see the very basic thing, which is your fluorescent screen, which I have zoomed into here. So this is how a fluorescent screen looks like, and typically you have this coated with a fluorescent material, and when the electron beam strikes this fluorescent screen, you have emission of light within the green wavelength, and you immediately see whatever interactions are happening directly on this. The fluorescent screen camera is extremely fast. The fluorescent screen is extremely fast. The fluorescent screen cameras which are there in modern day microscopes are not as fast as the fluorescent screen yet. But the first level of information you record before you start storing it on a photographic plate or an image plate or on a CCD camera, you see it on a fluorescent screen. And there is also a mini screen which you lift up, and it comes up here, and you see with the binoculars, and you use it for focusing. And this is how a fluorescent screen is. You have some varying intensity that is a consequence of the interaction of the electron with the specimen, and it is displayed first here on the screen, and this is lifetime. You can now record it with fluorescent screen cameras as well, but in the olden days, so you can see this lever here which pops up another small screen, and you use this for typically focusing, and you see the first level information recorded here, whether it is an image or a diffraction pattern. Once I have an on-axis camera which is aligned with the optic axis of the electron microscope, or sometimes you have some retractable cameras, or you have an EELS camera, you typically use a CCD camera. I'll just show you the basic construction of how a CCD camera looks like in the next slide. You record the information. There are a few important parameters here. You should know what kind of dosage you can allow onto your camera, what are the exposure times, what is the appropriate imaging condition such that you do not damage your CCD or your CMOS camera. The direct electron cameras and the modern day high speed cameras like the Gatan K2 or K3 are extremely expensive, and if you use high doses of intensities, especially when you're doing diffraction, you can damage your camera in no time. So please bear in mind that be kind towards the recording medium and be kind towards your facility manager, and follow the instructions and find out what are the allowed ranges of intensities and the the recording times if I want to obtain a frame or if I'm obtaining a image series, and please stick to them. So if I look at the CCD camera, the typical position of the CCD camera is like this on the microscope column. At the bottom, you have typical bottom mount cameras. These can be retractable or on-axis cameras. In the system we have here, we have the Olympus Tengra basic CCD camera. And how does the CCD camera work? I have a charge coupled device. It is essentially a semiconductor. So you have a polysilicon gate. Your incoming electrons are hitting the polysilicon gate, and then you have a dielectric here, and you basically have a potential well. So at each pixel, whatever electron is hitting that particular pixel, you are converting the photon, or you are converting the electron, which the way you see on the fluorescent screen camera, to a digital signal. This is either converted to a 0 or 1 or 0 or 255, depending on how you are storing it, and each of this is now again converted to a node. Through an output node, you actually convert it into a digital signal and you store an image. There is a lot that can be discussed on this. I just wanted to give you an idea of where these are located within the microscope and what are the precautions you need to take. The complementary metal oxide semiconductor cameras are more commonly used now, and they have a better dynamic range than the CCD cameras. And these days there is a lot of interest to use the CMOS cameras also for more advanced imaging modes such as 4D STEM, where you want very high frame rates for recording. You are nowadays using microscopes for also performing in situ TEM studies, where you are not just recording a single image. So the quality of images that you were recording on CCD cameras was quite good, but the frame rates were quite restricted. You typically had frame rates of something like 2 or 3 frames per second in the best case scenario, to about 20 or 30 frames per second. But nowadays, with the CMOS kind of cameras, you can also achieve easily 200 to 300 frames per second. And there are some specialized cameras like the K2 and K3, where you also achieve 1600 to even, I think there are almost about 5000 to 6000 frames per second cameras also available these days. But this is not for the entire size of the detector. When you bin it down, or when you have only a small portion of it, you are achieving higher frame rates. So there are a few parameters here when I talk about recording information and storing it on a photographic plate or on a camera. These are primarily the brightness or dose of the electrons striking the camera. The second thing is your exposure time, and you can control these either by playing with your aperture sizes. Typically you can use a smaller condenser aperture to allow a lesser amount of electrons to propagate through the column and then strike your detector. You also control something called as the spot size. Typically the spot size is counterintuitive. The numbers from 1 to 5 or 1 to 9, the larger the spot size is, the smaller the brightness or the beam currents are. Especially for low dose imaging, you use higher spot sizes, and you should also be very careful in checking where your field of view is and where your alignment of the camera with respect to the microscope column is. Typically it is more or less on axis, but there may be cases where the information you see on the fluorescent screen might be slightly displaced on the camera. Please check where the sources of these errors are. Is there any kind of an image shift, or is there some physical misalignment, or so on. So identify a recognizable feature on the screen by placing an aperture halfway before you record something from the feature of your interest on your specimen, and see where it is positioned, and check not the entire area of the fluorescent screen is typically the size of your detector on the CCD or CMOS camera. Look at all these parameters, control the dose, control the exposure time, control the frame rate, and record the information. This is one kind of detectors we have. There are also other specialized detectors like the HAADF detector, and you also have the DP stem detectors now. We will look at it when we look at different modes of imaging, when we touch upon the detection of stem images. But for now, that is all we have on CCD cameras and the location of them. We will move on to see what kind of specimens are allowed, different specimen preparation techniques that we use for transmission electron microscope. So now let's have a look at the kind of specimens that can be used in a TEM. I mean the kind of specimens that can be analyzed in a TEM. If you recall, I was mentioning that within a transmission electron microscope, there is a limit on the thickness of the specimen. In the very introductory lectures, we mentioned that one of the limitations of TEM is you see projected information, and in addition, preparing a specimen is challenging because not all materials will allow electrons to pass through. There is a strict limit on how thick the specimen can be. Typically for most of the inorganic materials, this number is approximately the size of 100 unit cells stacked one over the other. And if I assume the size of one of the unit cells is approximately 10 angstrom, so stacking 100 unit cells would give you a thickness of around 1000 angstrom or 100 nanometers. And this is a ballpark figure for an element with an average atomic number of around 10 to 20, which gives you a reasonably good specimen thickness. As the atomic number increases, you want the specimen to be as thinner as possible. The reason being, you cannot have the electrons propagating through any thickness. You wouldn't get good enough contrast, and you cannot often achieve high resolution. And there are a few pleural scattering effects or dynamic scattering which will give you some kind of challenge when you are trying to do any spectroscopy as well. Let us now focus on common specimen preparation methods and understand what is being done and how a common specimen geometry for transmission electron microscope looks like. So the most common materials that you can study are metals, ceramics, polymers, thin films, powders or nanoparticle suspensions. You can also look at biological specimens, proteins, cells, tissues, 2D materials, which is one of the most happening areas now. So the 2D materials are perhaps the most ideal candidates for TEM because they are usually 1 or 2 atomic layers thick. But the other class of materials that you see here, metals, ceramics, composites and polymers, you would have them in a pretty bulk sized, you would have them as large bulk specimens, and you would want to thin them down and make them small enough such that they can be introduced into the microscope column. If you recall, I was mentioning that the microscope column diameter is typically of the order of a few millimeter, so not all kinds of samples can be studied within a microscope. In general, the TEM specimen preparation philosophy is such that you take a large sample, you section it, you grind it, you thin it down such that the dimension along the z-axis or along the optic axis of the microscope is less than 100 nanometers. If you have metallic samples which are conductive, there are methods such as electropolishing which you can use to thin down the specimens by simple dissolving the metallic sample by making it as an anode and having a jet of electrolyte. This is perhaps the most common and the simplest methodology to prepare specimens. If you have ceramics, the good thing is you can crush them, you can grind them, make them as small as possible, and you can create a suspension of the same, and you can disperse it and you can image it. Polymers are slightly more challenging because these are also highly sensitive to the electron beam. Although you can have slightly thicker polymer specimens, and the same applies to biological specimens as well, you are always limited by the dose that these polymers can withstand or the biological specimens can withstand. Thin films, you commonly study them by sectioning them. You would want to look at the cross section of the specimens. Thin films are typically grown on a substrate, so you have to cut them such that the thin film doesn't get delaminated. You section them, polish them, bring down the thickness, and you have to do some final special methodologies such as ion milling. Powders or nanoparticle suspensions are perhaps the easiest among all. You have a ready-made suspension. If you can ultrasonicate the suspension without causing any damage to your sample, you typically ultrasonicate this, disperse the nanoparticles more or less uniformly, ensure that the concentration of the suspension is not too high nor too low, and you drop it onto a grid, and then you can use it for imaging. 2D materials are kind of ready-made specimens for you. If you can transfer them appropriately, you can then use it for doing TEM analysis. Let us go through some of the classic specimen preparation techniques. I'll give you a quick overview of the various methodologies, and we'll look at the specimen geometry and how is it inserted into the microscope. So if I look at the easiest case, like I was mentioning, you have the nanoparticle suspensions or powders. So the ceramic particles, you can simply take a mortar and a pestle, or if it is allowed, you can do ball milling and you create powder samples and you disperse them. When you're dispersing these powders, please ensure that the suspending medium that you are using evaporates reasonably fast without leaving any residue. The challenge with these kind of specimens and the liquids that you use, for example, you can create a powder from a ceramic sample. It could be any oxide. For example, let us say I prepare a specimen of zirconium oxide. I can crush it, grind it, make a small powder, but if I suspend it in a kind of a medium such as ethanol or acetone or any other organic liquid, you would want to ultrasonicate them and disperse them on a grid. We'll see the common geometry of a TEM grid in a couple of slides when I talk about specimen holders, but ensure that the suspension is uniformly dispersed and the particle density all across the TEM grid is more or less uniform. These are usually trial and error methods, and on experience you would know what is the right concentration to get a very good suspension. So the usual steps are, you can grind the specimen, you suspend it, and then you drop cast using some kind of a pipette like this. Before you drop cast, you ultrasonicate it in an ultrasonic bath, and then, like I was mentioning, the common solutions you use to suspend are ethanol, acetone. Acetone is slightly more reactive. We use isopropyl alcohol, or something which is very interesting is hexane. It is very important that you choose the right kind of suspending medium because if I do not let the suspending medium evaporate completely, if I have any trace of any hydrocarbons from any of these solutions, you would have something called as hydrocarbon contamination. So, if I have powder particles which are lying on a grid, if I have a monolayer of any of these organic residue on this grid, under an electron beam, you would have cracking of these hydrocarbons, and typically you are left with a nice carbon layer deposition on the surface. So, the usual practice is, if you can, you suspend them and do a very low power plasma cleaning, or if you can heat or use an infrared lamp, kind of let all the suspending media evaporate, and you would have a reasonably clean specimen. So, that is the easiest way in which you can prepare the specimens. The next method that I was mentioning was electropolishing and ion milling. This is commonly used for bulk ceramic or composite specimens. You can also use it for thin films where you want to prepare cross-section specimens, or for metallic samples. The whole idea is, before you do the final step of electropolishing or ion milling, you take a bulk sample. Let us say this is of the order of a few millimeter cube. You section out the sample either by using a diamond wire saw or a low speed diamond blade cutter, or if it is a semiconductor sample, maybe an ultrasonic cutter. You have to section these and ensure that you have a handleable thickness of the specimen. You should be very careful if I am preparing a cross section specimen of a thin film. So, if this is how my substrate and the thin film on the top is somewhere here, more often I want to view the specimen along this direction. So, I should section it in such a way that I obtain a small slice which has the thin film and the substrate interface retained. There are ways in which you can carefully prepare this. If it is a metallic sample and you are not too concerned about any specific location or a region, you can always grind them, cut them, use the usual routes of metallographic specimen preparation, and the whole objective of this first step of sectioning or cutting or grinding or polishing is you reduce the thickness to a range of plus or minus 100, 50 or 20 microns. From 100 micron, or let us say in the best case scenario less than or equal to 70 micrometer specimen, you can punch out small discs which have a diameter of 3 millimeter, and you electropolish them, which is what we will see in the next slide, or I can dimple grind them. I think there is a schematic of a dimple grinder coming up next, but the idea is, if I have a specimen which is like a disc, either by electropolishing I kind of make a hole in the specimen, or with dimple grinder I am reducing the thickness in this area such that I can create a crater or a dimple, and I make it sort of a concave shape, and I reduce the thickness around the central portion of the specimen to less than or equal to 20 microns. The next step after you dimple is you can do ion milling. Typically you use argon ion mill, and there are various energies with which you can operate such that you can create a hole. So, if I talk about electropolishing and ion milling, the simple step of electropolishing is this. You can use only for conductive specimens. I make the sample after I cut, section and grind and punch a 3 millimeter disc. I make it as an anode. So, my specimen of interest is anode. Usually you maintain the electrolyte which is used for electropolishing at a specific temperature. These can be anywhere from minus 30 degrees centigrade to plus or minus 20 degrees centigrade, depending on the medium that you use, depending on the material that you are looking at. Most commonly for steels or metallic sample, the most common electrolyte used is 30% or 20% nitric acid in methanol. You usually maintain them around minus 20 or minus 30 degrees centigrade. And the idea in an electropolishing system is the specimen stays suspended vertically, and from either side you have two nozzles through which an electrolyte is spraying a jet. You want to use very high current densities here because you want the process to happen very fast. So if I have a disc which is thin and suspended vertically, I want to create a hole by removing two jets of electrolyte from the sides, and then I end up with a gap and I form a hole, and the specimen has this kind of a geometry. Here is the cross section. So you are creating some kind of a specimen like this with a small hole in the center, and right next to the hole you have a wedge shaped sample which has a thickness less than or equal to even 10 nanometers in some cases. So a typical electropolishing setup looks like this. Here is where the cartridge is, where you load the specimen, and this is made the anode, and you have two jets shooting from the sides which kind of make the hole. In fact, the jet direction is like this in this figure. Moving on to a dimple grinder. This is how a common dimple grinder looks like. Please ensure that the rotation speeds, the suspension that you use as a grinding media, the rotation speed of the turntable, the rotation speed of the grinding wheel itself is such that you do not cause any delamination of thin films. So you place a very small 3 millimeter disc which is having a thickness less than or equal to 100 micron here, and with the rotatory motion of these two, you are essentially creating a small dimple shaped specimen in the cross section like this. And here the thickness is 100 microns or lesser, and in this region your thickness is less than or equal to 20 microns. Quite often a very bad practice is you do not check the thicknesses after you dimple, and this can have a severe detrimental effect on the ion milling systems you use. And moreover, the thinner your dimpled area is, the shorter the milling times are and the better quality specimens you get. So here is how a common ion milling system looks like. This is the Gatan PIPS 2. There are alternative ion milling systems as well. I think there are systems from Leica, Technor Glinda, and Fishiona, Hitachi. I think even Geol has one. There are quite a few systems like this. But the idea is when I have a dimpled specimen like this, if this is suspended on a rotating stage inside this chamber, I can shoot ions from the top and the bottom if you have a dual gun system. So here are the two guns, and when a beam of argon ions is impinging on the surface, I start forming a hole here, and like I showed in the electropolishing system, the thickness goes down further and further, and I form a kind of a wedge shaped specimen with a hole at the center. And this region You have to search for this hole in a microscope typically, and right next to the hole you have the best thinnest region. Identifying the thinnest region, orienting it in the right orientation and all matter a lot, and preparing specimens with as low artifacts as possible makes it very important. So the common artifacts you get, so the common artifacts in specimen preparation are, in electropolishing, you may oxidize the metal a lot, and you can have amorphous or in sometimes a few crystalline oxide layers right next to the hole. So please be aware of this. It is good if you have an amorphous layer because you can use this for alignment in your microscope, but if it drastically changes the local chemistry of your sample, you should really tune the parameters really well. And with ion milling, you can always have areas which are strongly impinged by the argon beam, and you can have also amorphized regions here which often may not be the meaningful information you get from a specimen. So please be aware that there can be artifacts during specimen preparation, and be careful in interpreting the data that you get. The next kind of specimen preparation method commonly used for biological specimens is something called as vitrification. So the idea is, you have a system like this is called as a vitrobot. For biological samples, typically you use specimens which are very sensitive to the electron beam, and these are often imaged using a cryotransfer holder maintained at liquid nitrogen temperature. And one of the most common problems with biological specimen preparation is you typically have some kind of an aqueous medium, and you do something called as plunge freezing or vitrification here, where you drop the suspension of your biological sample into a bath of liquid nitrogen. There is liquid ethane being circulated around to maintain the liquid nitrogen temperature constantly, and this has to be done really fast, because if I do not cool the liquid really fast, if I do not quench the suspension, I do not get amorphous ice, because typically you have aqueous suspensions and you might have crystalline ice. If ice is cooled slowly, it can crystallize as hexagonal ice, and this interferes or gives you a background while you are imaging. But for biological specimens, in the best case scenario, the idea is we place a specimen on a grid between these two pads that you see here. You have some blotting paper discs here. You just introduce a liquid suspension from this hole on the side. You just drop cast it onto a vertically standing grid. Gently you blot away the excess liquid using these two blotting discs, and then you plunge freeze it. Before preparing specimens, you typically do something called as glow discharge of the carbon grid, so that you make the grids really hydrophilic, and when I drop a liquid on it, it spreads in a large area. All these methods that I have spoken to you till now involve a great amount of patience, skill, and experience matters. If you've had any of your group mates who have prepared similar kind of systems before, you please discuss with them on which scenarios do not give you a very good sample. So once you prepare these kind of specimens, you can take them to the microscope and start imaging. There are a couple of more advanced methods specifically for site-specific specimen preparation, where you use a gallium ion beam, and I'll just show you a couple of examples of how cross-section specimens are prepared in the next slide. So commonly, you typically have a dual beam focused ion beam and SEM. These are called as the dual beam or multi-beam or any of these kind of systems. The idea is, in an SEM, you have a SEM column, and at an angle of 53 or 54 degree, you have a gallium ion beam column. Typically, this is a field emission gun source, and here you also have a tungsten filament, and in front of the tungsten filament you have a liquid metal ion source. Commonly it is gallium. Nowadays there is something called as a plasma fib. You can use xenon, or if you want a very high resolution, you can also use helium ion to actually impinge and remove material. So the idea is, the momentum of heavy gallium ions which are accelerated in this direction, they are focused into a small probe. So in an SEM, it is a raster based technique, so you have to converge the electron beam to a probe. You find your area of interest. So if this is my area of interest, this is from an aluminum sample, I can remove one of the top layers with a gallium ion beam. You typically call this as ion etching. You might or might not want to do this depending on the kind of specimen you are preparing, and what you then do is, you deposit a protective platinum, tungsten or carbon layer. Once you identify the region of your interest and you deposit the protective layer, which is typically a heavy metal, you start directing electron beam, you start directing the gallium ion beam to form trenches around your region of interest. So you remove all the excess material from this region, and you end up with a situation like this. You can either prepare a very thin specimen in the trench like this. In the olden days, when you did not have manipulators, you typically use the glass needle to pick up this very small specimen. So from a bulk sample, after identifying a region of interest, you have to section it, go down step by step, and prepare a specimen where your thickness is less than 100 nanometers or 80 nanometers, or as thin as you can make it. So here is how a typical thin TEM specimen looks like. If you have an in situ manipulator, you can section this, lift this out, and do even finer thinning and get a very good quality specimen. A focused ion beam coupled with a cryo stage also allows you to prepare biological specimens as well. This is a very powerful site-specific specimen preparation technique. Now, moving on to further techniques that are available for biological specimen preparation, you have something called as ultramicrotome. So the idea is, typically for polymer samples or for biological samples, you have a sample block on which you fixate your thin specimen. You should be very careful with the direction in which you want to have a cut. The idea here is, you have a sharp knife which is typically diamond knife, and the edge thickness of the knife is less than 50 nanometers as well. So you want to make a very sharp cut instantaneously. So what happens is, you place the knife on a trough and a holder like this on, so you fixate the position like this, and you have a sample block which moves very quickly. So it is like you are chopping vegetables or meat with a sharp knife. You just give a quick cut and you remove a thin layer. So typically the layer's thickness here is less than 50 nanometers. You can also get 20 nanometer sections, and this technique is most commonly used for, I should call this as cryo ultramicrotome. for biological specimens or polymer specimens. You should be really careful in how you again prepare the parameters, how you cool it. These are all kind of automated these days. So once you know you have a very good knife and everything, so you have a fresh knife, sharp knife, you have to be careful. If you are using a pretty used up knife, you might end up with getting poor quality specimens. One important precaution that you need to know or learn is, with any of the methods that you prepare, please stick to the prescribed procedures and do not be a trouble to the next user. Try to section them, try to prepare the specimens and clean up and retain it or restore it to the previous condition in which you received these specimen preparation tools. So in ultramicrotome, the idea is you're just chopping off a very thin layer and you section it out and you transfer it to a TEM grid. Once you transfer the specimens, which are typically of the size or the diameter of 3 millimeter, you put them into TEM holders. This upper limit of having a specimen thickness of this upper limit of having a specimen diameter of 3 millimeter has simply been fixed by the diameter of the microscope column, the inner bore of the microscope column, and also the space that you have in the specimen holder. Conventionally, the pole piece gap has been less than 2 or 3 millimeters, and you would want to have as high tilt as possible with the specimen holders. With these different kinds of specimen preparation methods, I would advise please be very careful in following all the protocols and prepare as thin specimens as possible. And a good practice is to prepare numerous number of specimens with the same kind of preparation strategy, so that you would get some meaningful data from one particular analysis session. With that, let us move on to the common specimen holder types and understand why these specimen holders have these geometry. So the most common specimen holders are the very common single tilt or double tilt holders. If you are looking at biological samples or thin film suspensions, for a quick check, if you have a good specimen prepared, you might want to go to a standard single tilt holder. If you want to do some advanced crystallographic analysis, some specific imaging in particular orientation, or do high resolution studies, or obtain EDS or spectroscopy, be it yields or any other information from a material, you might want to use double tilt holders. There are also special holders where you can do real-time imaging in microscope. You can use the holders to apply some stimulus onto a sample. This external stimuli can be like heating, biasing, deformation, or applying a magnetic field, or maintaining an extremely low temperature, even down to liquid helium temperature as well. You're not going almost into a liquid helium temperature like a squid, but there is reported literature where you've achieved 5 to 10 Kelvin as well. So the geometry of a specimen holder looks like this. This is how the geol holders look like. The other instrument manufacturers have slightly different geometries, but the main idea is you want to introduce a specimen from ambient 1 bar vacuum condition into a microscope column which is maintained at ultra high vacuum. So a few critical components of this are the bay where your sample sits. As you can see, there is typically a Viton O-ring. You should maintain this entire portion of the specimen, in fact the entire holder, extremely clean. So you have a rod and you have 2 axes of rotation. You have one axis along the axis of the holder and the other axis of rotation which is possible here. So with this, typically you can achieve a limited range of tilts and you can orient the specimen in different orientations and start imaging. As I was mentioning, the diameter of the specimen has been restricted to 3 millimeters, which is the most common type, and for some specific cases where you are using cartridges for vitrification and all, you might also have 2.3 millimeter diameter specimen holders. For some special holders where you want to use holders with rotation and tilt, you might want to have different kinds of specimens. You might be using some tomography holders where you want to fix a needle in the tip of the holder. So you might use needle shaped specimens with diameter less than 1 millimeter at the base, and it might narrow down to less than 50 nanometers at the tip. So there are different kinds of holders. So the idea is, you have a typical TEM grid which looks like this. You drop cast a sample onto the grid, you insert this into the specimen holder in this gap here, and you introduce it into the microscope column. Most importantly, do not touch any of these with bare hands. You may have some residue or some dirt from your hands which can trap onto the tip of the holder, or it can trap into the O-rings here, and this prevents you from achieving a very high vacuum. If you recollect this image, here is an example image again of your split pole piece within a microscope. The holder front part goes into this gap here, and you end up getting a limited range of tilts. Once again, the tilt that you can achieve is restricted by the gap you have within a microscope pole piece. And most commonly, the X tilt or alpha tilt is limited to plus minus 30 degrees, and the Y tilt or the beta tilt is restricted to plus minus 15 degrees. You might want to discuss with your facility manager on what kind of holders you can use for which type of an analysis. And please be very careful. These holders are usually extremely expensive, and they should be handled carefully, and they are extremely delicate. And in the demonstration sessions that follow, you will see some few safe practices of handling these holders. If your instrument allows a large enough pole piece gap, or if the holder geometry fits in with the existing pole piece gap, you will have multiple different kinds of holders which you can do some real-time imaging in the microscope. Here are a few examples of most common commercially available real-time holders. I think here are the holders from a company called Hummingbird, and this is from a company called Protochips. This is from Melbuild, and these are from the company called Dense Solutions. The idea of using these kind of holders is, you can get in an electrical feed through, you can get in a liquid channel or a gas channel to flow through, and with the advent of MEMS based technologies now, you are replacing the classic copper grid with a MEMS chip here, and in the tip of the holder, with the electrical contacts that you have, you can apply different kinds of signals. You can do biasing, you can do 3 electrode measurements like in an electrochemical cell, or a 2 electrode measurement depending on what you want. You might have different kinds of holders where instead of a specimen being a chip here, you may have a small needle like an AFM tip. So you can also do AFM or indentation within a microscope column. You can have biasing, you can apply a heat, you can heat the specimen to temperatures as high as 1300 degrees centigrade, and while all these changes are happening, you can study and record movies of how the material properties are changing with an application of external stimuli. So that is all we have on different kinds of specimen holders and specimen preparation methodologies. I would advise, please discuss carefully with your facility manager and follow all the precautions before you start using these different kinds of holders, and good luck in preparing good specimens and achieving the best possible results. Following this, we will see how a specimen holder is loaded and how you start obtaining some basic images in a transmission electron microscope. Thank you.